changed his name because Hollywood.
I see. Yeah, I was trying to. And this is back in the time too, right?
Yeah, this is probably the 60s. But it's a very diverse town, which you would not expect in the middle of the Midwest. But
Correct. Yeah.
it's rather interesting to go to a lake shore that you cannot see the other side, because it's so huge. It's the Great Lakes. The Great Lakes, like one of like Erie or Michigan. It's
It's not very common, right? These huge lakes.
no,
At least Ukraine is on one of them, right? Like that is in the news. I think isn't that also a lake or maybe it's a sea?
I'm not sure if it's a.
Is it a lake or a sea? Ukraine's. They call it black. I mean, is it black? I don't know. Maybe it's other.
Is it Black Sea? I think so. Yeah. I know there's some inland lakes in.
It looks like a lake though, but probably it's sea. The history goes that all the whole Mediterranean was a desert, and then or it was a bigger sea, and then it got
Landlocked.
landlocked, kind of something like this. So I posted a new homework. And this is due on the same day as the exam. Is that fine? Is that acceptable?
This one being exam.
Yeah, we have. Oh, is this on the exam?
No, this homework.
Yeah, let's have it on the. I'm open for suggestions. Does it hurt a lot when you have the homework due on the same day as the exam and the syllabus or the exam syllabus contains that? No response, which is okay. But you don't have it.
I think several of us are still working on homework 7.
Yeah, I know. So because that's a fear. I mean, if I say it's not in the exam, then it's very natural for you guys to do it after the exam, study for the exam. So,
I mean, if
so
it's
let's
gonna-
catch up, kind of. Is that a yeah, that's the discussion that, yeah, I mean, I'm saying yes, but I'm open for suggestions.
So the homework 8 is going to help us in exam.
I'm saying it's included in the exam. but help us in the exam, it depends on how many questions I ask on that. Right? My motivation is more to make you guys catch up on things. If it is in the exam, then you will catch up with that. But I mean, I feel like, yeah, okay, maybe I should not ask too much because it's so close to the exam, but that doesn't mean that I will not ask. Right? So, does it help? That's harder. I don't know the questions yet. Okay. And I sometimes think that I should make a longer problem which can be take home, but I usually think of that, but then I end up doing it, not doing it. It requires more preparation time. So the answer to that is yes, it might. Okay, so we go by that. No complaints.
It's hard to have an opinion because we haven't looked at homework A yet. Is it, what's the,
You asked me.
well, I mean, what's
Yes.
the focus of the,
Poisson brackets. I think it is relatively little tedious, of course, but it's less. Once you get the concept, that's all there is to it. The details are, for example, in the variational calculus, there could be things missing. There are 2-3 ways of doing it, and it's very easy to miss on something and still get the answer. You might cheat yourself with an argument and do something and get an answer, which is correct because the details doesn't affect the argument so much. So in that sense, I feel it is harder. But Poisson bracket, I think, is more clean. Or maybe the words used, I can use this, it's less error. In that sense, maybe better. And I don't have so much experience either. Like I ask questions, but I don't remember which questions students get hurt. Like in undergraduate physics, I really know that, okay, if you ask energy problems, students do better. Force problems, they don't do better. So it's a bigger picture I guess, because it's maybe it is a number of students. I don't get a clear idea of which topics are easy and which topics are hard. Like for example, I was thoroughly surprised when I found that functional derivative was so hard. Like when I see from my perspective, it seems like it should be easier, but that's a difference between the students and the instructors.
This is the last session for the exam or Tuesday?
Tuesday is the last session. We'll have one more lecture. Yeah. And yeah, that brings to the other challenge that I have. I decided to do this Poisson bracket, but then I have this limited time. So I have to do something in that period, and I don't want to stretch it really beyond 1 week because everything else will get affected. So I'm going to really shorten this so it won't be too detailed, but still I want to convey the idea as much as possible. Okay, so the first thing is we did, and this should have come before your homework 7 that is due today. I wrote the whole of homework 7 in terms of the Hamiltonian, but we wrote did the class calculation in terms of the Lagrangian. And the difference is very tiny, that the equations of motions has a small extension to it. But those equations of motions are crucial when you go to the next step, which is the Poisson bracket. So I feel that I will very quickly go over the whole thing for the Hamiltonian formalism. It might, at least the ideas might be repetitive, but maybe it will enforce it better. And then use that to, in a very simplistic manner, say what's the motivation of Poisson bracket. And Poisson bracket is only one piece of the story. It is like saying in quantum mechanics, often we think of commutation bracket as simply an exercise, but it is one way of looking at it is that it is a calculus of quantum mechanics. Calculus in the sense you make a small change in an operator. What is the corresponding change under certain transformation? Usually when we say a change, we talk about rotations or translations, or under a boost, what happens, or under an energy transformation or a translation in time, what happens. When it is translation in time, that is the most interesting part. You say it is the evolution of the operator. But one can do this for any operator. And so it leads to a whole set of commutation operators, and it's kind of a nice generalization to have. But I will barely touch on it. I will just say that what is the idea of commutation relation, which shows up here as Poisson bracket. So the ideas will be very much in there. And in your homework, you will see the connection between the Poisson bracket and the commutation relation. And it was, I think, first time observed by Dirac, who actually started the whole thing. And even today, I feel that is the best description even today. It's a very clean, simple description. So I made it a homework. Typically, I make it a homework and just follow it up. It is a few steps and just follow it and see the connection. Okay, so as I said, I'll go back and sort of repeat whatever we did in the last two lectures in the Hamiltonian description. So just get the backdrop. All right. Okay, so we have our action, which depends on the position as a function of time, and it depends on the endpoints T1 to T2, and this is equal to T1 to T2 dt. Now, and we have been using velocity also for this, but whenever we put in velocity, we should remember that that's just a notation. Here, R is the free variable. Whenever we change the R, it is the R that changes. V doesn't change on its own. The change in V is due to the change in R, and that is time t. We have the definition of canonical momentum in terms of the Lagrangian as dL by dV, and V is, as I said, it's a notation. There are formal descriptions where V is also upgraded or lifted up to a free variable, and then you get three equations of motion. Equation of motion with respect to position, momentum, and velocity. So that's also a possible scenario, but we are doing the Hamiltonian description, which is the most symmetric form, I guess. Once we have the momentum, the Hamiltonian is described as it's p plotted with the velocity minus L. And in this manner, it seems like the Hamiltonian, so Hamiltonian here will depend on R by dt, because Lagrangian depends on dr by dt, and there is a p here, and it should depend on p, and there is a t, right? That's your velocity. What is the partial derivative of the Hamiltonian with respect to velocity? Zero, because it does not depend on that. We have shown earlier that the Hamiltonian does not depend on the velocity. It always depends only on the R and P. So that's equal to 0. So that implies that H is equal to H of R, comma P, comma T. And then
V, it's P dot V minus L.
it is P dot V, but V is dr by dt, right? Does it look like V? Sorry, this is R. Is that a confusion?
It's V, dr.
Help again? Help?
It is P dot V minus L.
Yeah, that is what it is, right? This is V.
Why is the derivative of 0?
Oh, why is it 0? Yeah, good question. Oh, so that's your point. How is it 0 when you can see the V out there, right? So it doesn't make sense. So let's see. Okay. So yeah, so let's see this. So H, we don't know what it depends on. The guess is that it depends on velocity also, or it seems like it should depend on that. So this is P divided by dr by dt minus L of R by dt times t. So there is dr by dt here, and there is a dr by dt there. So do the, I mean, take the simple derivative. That's also good enough. Partial derivative with respect to velocity is one is here, that gives you P itself, that's P, and minus the derivative of this with respect to velocity, right? So dl by dv, right? But by definition, P is your partial derivative of L with respect to V, so that's equal to 0. So that's one of the important player in that this is called the legendary transformation. This construction always leads to the fact that one of the variables will be gone in that construction. Always, if you have this, this is called the legendary transformation. It doesn't have to be in this context that it is Hamiltonian and Lagrangian. If you get a chance to look at thermodynamics, again, you will see that all the constructions there, they go from one to the other, always using legendary transformation. You can start from L, you get H, you can start from H and again construct another variable and keep going, and you can get about 3 or 4 situations. Another construction you can have, maybe quiz, right? So a quiz. What about, let's say, yeah. Let me do the opposite, right? So L is equal to P divided with dr by dt minus H. And let's call this L R. Calculate L of P and do it this way. This is dP by dt, R and V, yeah, dP by dt divided with R minus H. And for reasons that's not obvious at this point, put a minus sign also. So calculate this Lagrangian and see or construct a, find the equations of motions in terms of this Lagrangian. That's it. And this is typically done, and like in especially I think in quantum mechanics, there is a symmetry between these descriptions, and it's good to analyze. But Yeah, just as a curiosity, you could try that. Okay. So that's H with respect to V. And that means that we can actually go back to our action and this time write the action as R. And once you write it in this form, it is also possible to have your P independent of R, even though the construction is that P is in terms of the Lagrangian and derivative with respect to V. If you set it to be independent, arbitrary variations again, then you can have T1, T2, T, and this is T. H or T, T. Remember that R is a function of time, P is a function of time, and this is an integral on that. Make the transformation in R, P, and time all together. So we can say R plus delta R, P plus delta P, T1 plus delta T1, and T2 plus delta T2, and that will be equal T2 plus delta T2. Now we have dt. The integral parameter is dummy, so that doesn't change under this transformations. We have P plus delta P now. D by dt R plus delta R. And minus H R plus delta R, P plus delta P, and T. Like make this change and then subtract out the initial part, and that's what we have been doing all through, right? That will be the variations in a sense. Before we proceed to subtract, it is good to move the variations in the boundary is onto the function itself. So for that, we substituted T prime is equal to T minus delta T of T, and we require that delta T at T1 is equal to delta T1, and delta T2 is equal to delta T2. That's it. Like this is still arbitrary. This was an arbitrary variation, but that arbitrary variation is set to the arbitrary variation that you made at the limit. And this is a substitution you make. And this leads to the idea, like I won't redo this. This is dt prime times 1 plus d by dt prime of delta t. That was one thing we noticed. And the other is you will also need to change the derivative, right? Derivative operator that comes in, and it is good to is that d by dt is d by dt prime, and this is 1 minus d by dt prime delta t. This is d by dt prime. Okay. So if I make, so this is a substitution you're making. Like when we are working with integrals, we make substitutions. So I'm substituting t to t prime. So I'm switching over to that. And in that process, the limits change. And dt has to be changed to dt prime. And the derivative operator dt has to change. And this also leads to T1 plus delta T1 becomes T1. This under the substitution T2 plus delta T2 becomes T2, like when I substitute it in terms of T prime. Okay. That leads to action. This is the action plus the variation, right? Instead of writing this, let me write this as W plus the change in the action. Like there is always a piece of W in it. And that's equal to now T1, T2, dt prime. I have 1 plus d by dt prime. And you have, I have put in this t prime in there, otherwise most of it doesn't have any explicit t dependence. So this is p plus delta p dotted with the time derivative now is 1 minus dt prime delta t, and next one is dr by dt prime, and this piece is that here is d by dt prime. So basically, I'm replacing this d by dt with this structure in here. So this goes in there. That's already piece that is really relevant, and and I should also do minus fh or plus delta r t plus delta p, and since I substituted t in terms of t prime, so this is t prime plus delta t.
So we don't add d by dt prime. The value of d by dt.
This one I did, right? This one?
Yeah.
That I put it inside here. Okay. Like it acts on this r, dr by dt prime, and then it acts on that. Is that clear? Ask me again if that's not obvious. Okay, I'll do this here. So d by dt of r plus delta r is equal to 1 minus d by dt prime delta t times d by dt prime of r plus delta r. That's your question, correct? That should be this dt prime. But now I open this up. So that's dr by dt prime plus d by dt prime, the change in the position. And that's that piece there. So it seems like there are 2 plus 2, there are 2 into 2 into 2, 8 terms. But again, remember, we have to keep only the leading term. So not everyone's contribution, only 4 of them will survive. Clear? Okay, so we'll now expand that. So change in action. That's equal to prime. Let me proceed a little slow at this point. So this is 1 plus d by dt prime delta t Okay, I have P dotted with dr by dt. Right, that's, then I get this, and then what? I can have delta P multiplying that. So that's plus delta P dotted with dr by dt. There should be 4 pieces that is of leading order. So that's P, one of them. And then I can get this multiplied by this multiplied by this, and this again. Right. So let's see, P minus P dotted with dr by dt prime and d by dt prime of delta t. So that's basically this multiplying with this and this multiplying with this. That's one more. What is that? Is this one, right? This one multiplying with the leading ones, and that is minus or plus P dotted with d by dt prime of delta r. And that's the 4 pieces. Okay, and we have this we can expand now. So this is minus of h itself at r, p, and t minus delta r dotted with partial derivative with respect to r, delta p, partial derivative of h with respect to p, and minus of delta t, partial derivative of h with respect to. Hopefully that's clear. Any questions? Very similar to what we did last time. It's just this time we are doing it in the context of the Hamiltonian. Again, expand this out. In principle, how many? 1, 4, 5, 6, 7, 8 terms in a sense. Like 1, 2, 3, 4, 4 plus 4, 8, 8 into 2, 16 terms in principle. But when one multiplies all this, that's leading order. When this multiplies all this, most of them are second order. We just need to keep the p minus h term. So let's quickly write this down, and then it's just a matter of collecting. So when one multiplies out, this is p dotted with dr by dt minus of h. That's your leading term. So I've taken care of this times this. Then put everything else in a row. That's all. Still p r by dt minus p dr by dt prime times e by dt prime delta t. That's next plus delta p, mostly copy. That's multiplying all of them with 1. This takes care of all of this. And now when this multiplies, I don't have to worry about anything except these two, which is not having any leading variation. Plus p prime times d by prime delta t So let's modify these two, and finally minus h times d by dt prime. Delta t. I think this should be t prime. Everything is t prime, there is no piece at this point. There's only one small cancellation, but nevertheless, any cancellation simplifies. So there is this piece cancels out. Then we are remaining with 1, 2, 3, 4, 5, 6 pieces at this point.
So how we got the last two terms?
Oh, last two. Okay. First is I multiply this 1 with everything.
Yeah.
Right.
Right.
Now, when I multiply this with everything, this is already having a delta t. So I have to keep only those terms that does not have a delta t.
Right.
This one is there without a delta t. Right? That's this piece. This multiplying this. Okay. This one I drop because delta p, delta t. This is delta t, drop. Then there is h. That doesn't have a delta. So I write that down. Rest everything has a delta in it. So double and dropping. That's a very leading order, small, basically calculus, right? We are saying that only leading term contributes. This first term here, this piece, that's your action itself to begin with whatever we had. Subtract that out, that's your W. So the change in action is equal to collect things together, and especially the ones that is not with t prime. So let's say, let me remember we will have boundary terms, right? So I'll prepare this for the boundary term, or let's go slow. So this is delta p dotted with dr by dt prime. So next one is this here. This one, notice the variation in this case is inside the time derivative. I would like it to be free. Right? So I want to move this derivative on this to that. I do integration by parts. I do plus d by dt of p dotted with dr. But that's not what it is. It should be minus, right? So it is minus dp by dt dotted with delta. That's this second piece here after the removal of the action and the one that has already cancelled. This one is write it as it is. Move this here. Minus delta r dotted with h by dr. That's this piece here. Minus p that's also clean. And the next term that has the variation inside a derivative is the last term. So again, I move that out. That's minus d by dt of h t. This becomes plus. All these tiny steps, but yeah, it's tedious, long work, but mostly tiny, small steps.
Which one is prime? Which one?
Oh, it should all be prime. There is no all primes. Yeah, sorry, I think I have it messing up. Sorry. Oh, all of them primes. All of them are primes. There is no t that shows up at all. Or of course, this one is dependent. All the dependent variables. Independent variables. Integral variables. Or d prime. Okay, so collect them at this point, and this is T1 to T2 dt prime. And let me start with dr. Change in r. There should be two terms. That's let's start with r. So it's minus I dt prime. Those two have been taken care of. Plus the p, there are two pieces here. That's minus partial derivative of h with respect to t, and plus by dt prime. Next is T1 to T2 dt prime. Delta t also is dynamical variable in this doing it, and we have partial derivative time is equal to total time. And finally, the surface term. This is gone. That's gone. Or P. If you compare this with your Lagrangian, the only difference is that here you would have got the Euler-Lagrange equation. This would not be there because P is not independent there. And here, instead of the partial derivative of h, you would have got a partial derivative with respect to the Lagrangian, and this would have been a positive sign. That's the only difference. Again, if you say that boundary variations are zero, that means if these two are zero on the boundary, then you have the stationary action principle. So, doing shortcut here, stationary action, this stands for stationary action principle, with the idea that this goes to zero at the boundary. That's a standard thing. So then we have our equation here saying that dp by dt, that's your force equation, is minus. It's good to write this as a gradient, standard. The gradient of the Hamiltonian, and if the Hamiltonian is time independent, it would be the energy. So force is the negative gradient of the Hamiltonian. That's the first equation you can have. The second equation is dr by dt is equal to partial derivative of h with respect to momentum. That's the definition of velocity if you want, but more appropriately, this will be the momentum, right? This kind of describes your momentum, or actually, why say that? No, this is the equation of motion for t. This is the equation of motion for r and p are independent. This is how p evolves. This is how r evolves. That's our equation. And to again see the symmetry, I'll rewrite this. I wanted to highlight that's a gradient. This is dfr, right? So see the symmetry. P, the evolution of p with respect to time is given in terms of the partial derivative with respect to position, and is exactly opposite and with the signs coming in. And these are called the Hamilton equations of motions, and which is what we will use in this course. Mostly, there will be only 2 weeks, right? When we do Kepler problem, we'll start with those 2 equations. It's pretty much only at the starting point. Very quickly, you end up into the second order differential equation, and that's standard Newton's. There is one more, and again, stationary action principle. With the boundaries going to 0, you say that Hamiltonian, the change in Hamiltonian is given in terms of the partial derivative of the Hamiltonian. And that gives the idea that if the Hamiltonian is independent of time, if the Hamiltonian is independent of time, this is 0. Explicit dependence in time, that's 0. If this is 0, Hamiltonian is conserved. And if that is conserved, it's good to associate it with energy. Whenever you have a closed system, something is conserved, we know that it is energy, and we know that it has the dimensions of energy, then you associate the Hamiltonian with energy. If this is not, if this is time dependent, then this is not 0, then the system is not closed, and then you cannot define it as you cannot associate it. It is still the Hamiltonian, but it is not the energy because it's not energy of the system because it's not conserved. Okay. If all these equations are true, then we have, if all the stationary action principle is used up, then we still have a change in action. The system is evolving in this manner, and you can say the change in action now is, after all the under stationary action principle, this is T1 to T2 dt prime. This is contributing only at the boundary points. So we write this as p by dt primes of g of t, where that's g is called the generator. And this is t. This quantity here is nothing but g of t2 minus g of t1. So once you're actually on the trajectory which the system is evolving on, the action changes only at the boundaries. So the change in action is completely got by change in what we have defined it as the generator. So this is the generator. If you were to think of, let's say, a differential statement, let's say T1 is just T and T2 is equal to T plus delta T. That is, T2 and T1 is really close by. That's also a statement that you can read out from here. Then you have the change in action is equal to G of T plus delta T minus G of T. And that's nothing but in the leading order, that's delta T of in this case, since there is only T dependence. So this is by dt of G, which you could have read out right here, right? If you had, that's a definition of derivative itself. So the change in action, so if I put the dt onto the left, partial derivative of the action is nothing but total time derivative of G, if you will. So that's a statement which we will find useful, at least interpretation wise, but we're doing it in such a short time. And all the analysis that you did for conservation principles, you can do that here also, and it goes through. At this point, it is good to, I mentioned, so we have this generator, right? It is good to write the following. So we have seen that when we have a translation in space, right, we have del del R is equal to delta of epsilon. Right. And let's for a moment just work with delta R and delta T. And this is delta T is equal to 0. And correspondingly, you can decide for what's the change in momentum also. But for the time being, let me keep. So translation in time is delta R is equal to 0, and delta T. Did we use something for, what did we use for homework? Delta epsilon again? Okay, I don't want to use that. I'll use delta T. If that's okay. And translation, what else is there? Then we have rotations, right? Rotations, we call it rigid rotations. Rotations is delta R is equal to delta omega cross was it R cross delta omega? That was delta omega cross R. And finally, this is the new thing that you haven't, I did not give as a homework. You can also have a boost, right? By boost, I mean physics remains the same when things are moving with respect to each other. That's principle of relativity. Right? If I measure a system in my lab and then I again measure the same thing while I'm moving with uniform velocity, I still measure the same things. Or maybe I should say, certain things will change, like length will change, time will change, but there are invariant quantities when you put this together, which we will see in 2 weeks again in the special relativity. So there's a boost operator also, but let's stick to Galilean boost. Einstein's relativity is slightly different, and again here delta T is equal to 0. And this is change in, what would be the change in position due to an infinitesimal boost in Galilean relativity? What is Galilean transformation? Maybe let's begin with that.
X prime equal X plus VT.
Plus VT, yes. And T prime is equal to T, right? Let's make this R, vector R, right? And make this velocity V, right? And I'm making it infinitesimal. So the way to make it infinitesimal is to say that velocity is very tiny. That's a parameter here, right? Omega was angles are the parameter in rotation. This is the rotation. So the change is this minus this. So delta of R is equal to T times delta V. Right? That's a tiny infinitesimal Galilean transformation. And delta T is equal to 0. So here it is T times delta V, and this one is delta T is equal to 0. If you're doing Einstein's relativity, this will not be 0. That will be the difference. This will not be. Okay. Notice that there are how many pieces here? So there are 3 variables here. So this is actually a vector, right? There's 3 variables there. 1 variable here, delta T, that's only 1. there are three angles here, so that's three angles, and there are three velocities. That's good. Three velocities in there, and that's totally, there are 10 parameters. Overall, this together, now if I don't have to do this separately, I can put this all together. This will be delta R is equal to, add them all together, that's it. Delta of epsilon. So I make a translation, rotation, and boost all together. That's delta of omega crossed with R plus T times delta V. And delta T is just delta T basically, just the energy of these. This is called Poincare transformation. Again, in general, we are interested in knowing under when this happens, what is the change in your system. In particular, it is possible to write. So in your homework, you've seen this as a motivation. This piece here, P dotted with delta R, under this, it's clear that this will be P dotted with delta epsilon. In this case, this will be P dotted with delta omega crossed with R, but then write that as the angular momentum. So that's plus L dotted with delta omega. Again, this, if you have worked on the homework, it should be clear that why this is equal to this. It is actually P, so this is P dotted with delta omega crossed with R, but then this is the same as delta omega. What is this? Delta omega crossed with R dotted with P. Change the dot and the cross. So that's delta omega. Right, that's this. We are coming from. So, and then you have Hamiltonian minus H dt, and all this individually you have seen in your homework. You saw this separately, this separately, this separately. I'm just putting it all together. And finally, there is the generator with velocity or boost, which I did not give as a homework because it's slightly non-trivial. It doesn't come out immediately. And the operator there is called M. Doesn't have a name. Start with delta V. And what is N? It doesn't come out straightforward. If you were to do it using this analysis, it will come out as all this P, L, H is all fine. So your N is P times T minus M times R. So that's not very clear why that is, but we will leave that as a that takes in a good amount of effort. So how about this quiz, right? Whenever I want to leave something open, or whenever I want to skip something, I leave it to you. Right? What should I ask? What is N called, right? I think that will be needed. So what is N called? It doesn't have a name as far as I'm concerned. It's called a boost operator, I think. Boost is coming from because when you're moving, there's some constant velocity, boosting yourself in that sense. And here H is obvious, P is obvious, and L is the only thing that's remaining, so that's R cross P. So again, there are 10 operators. So the operators, so these are generators for the particular transformation, right? So P, L, N, and the Hamiltonian. These are called the Poincare generators. And you can, if you're doing quantum mechanics, you will do commutation relations of any of this P, comma L. What does it mean? P, comma N. What does it mean? That's each as a meaning. You ask the question: how does P change under rotation? How does L change under translation? Or how does L change under a boost? How does N change under a rotation? So you can ask any of those questions, and there are meanings associated with that. That I may not go too far. I will do a little bit when I'm trying to do the magnetic field. Again, crash course into one lecture, but hopefully I can give some motivations towards that. But in that line, so when I'm saying how things change, let us now. This is part of your homework. Only 10 minutes for your homework. Now I need to talk about how things change in general. Right? So instead of talking about the standard action all the time, so a system. Let's think of a system which is described by position R and P. And of course, there is time. Position, momentum, and time has been describing the system, and the Hamilton equations of motions, equations of motion, Hamilton equations of motion. Are dr by dt is equal to partial derivative of h with respect to momentum, dt by dt, that's force equation, it's minus h by dr is partial derivative of h with t. Notice the pattern. These are the three dynamical variables: total derivative of R, total derivative of P, total derivative of H. That's your Hamilton equations of motion. In general, you might have a physical quantity that depends, that is like these are the fundamental physical quantities, but you might in general have an arbitrary physical quantity. So let F, so a physical quantity, right? So a physical quantity. Since these are the dynamical ones, it will depend on these three quantities. So let's say F is equal to F of position, momentum, and time. That's a very general observable, if you want. And what you would be interested in is how does F change with time? That's what you would be interested in. And let's see, how does it change? So use the definition of derivative. So this is equal to the three variables. Each one can change independently. So first, let me write the time out. That's the explicit time dependence in F itself. But there is implicit time in R and P. So I have to do the chain rule now. So this is a partial derivative of F with respect to R and dr by dt. plus, and there's a dot product here, right? This is a vector, that's a vector. So there's a dot product in between. And momentum can also change. That could be time dependence inside of the momentum. So you again use the chain rule. And this is dp by dt. Is that clear, the motivation? Like you're interested in time evolution, and time evolution of a very general physical quantity is given in terms of this. But our equations of motion tell me that change in R and change in P with time, total time evolution is given in terms of the Hamiltonian. So replace that. Plus dotted with partial derivative of h with respect to P and minus and you see that there are these two operators f and h, not operators, two functions f and h. First you take the derivative with r and p, and then you swap it, and then you subtract it. So that leads to this definition. This is called the Poisson bracket. Any time evolution of any operator, not necessarily operator, I say operator because I'm thinking of quantum mechanics. Any observable is equal to the time, explicit time dependence itself, plus I will define, instead of writing it this way, I will write f h, and this is a definition here. This depends on r and p, so I'll write r comma p at the bottom. And just to differentiate between this and our quantum mechanical commutator, I write Poisson bracket on top, just to be explicitly clear that this is not the quantum mechanical commutator, right? So this is just to describe, to pay attention to the fact that we are in classical mechanics, and this is R and B. In general, I could do it with any operator. So f comma h, now definition. Is clear what that is. It is partial derivative of f with r dotted with partial derivative of h p minus of partial derivative of f with respect to p. Oops. You will use this in your homework. You will figure out what are the properties of this. This obeys what is called the Lie algebra, this brackets. So that's kind of nice to see. But like here in the last few minutes, let's do some simple cases. So f is any physical quantity. I could choose f to be r itself, the position itself. Right? That's a possibility. So let's say f. So let's do r comma h. Poisson bracket. Right? That leads to the partial derivative of r with respect to r itself. So that's one, right? But notice this is a vector, and I'm taking a vector, so it becomes the tensor, right? So this is one. Like you should be careful, right? This is delta ik. So this is one here. This is one. It's not a dot product. It's not three. And dotted with dh by dp and minus of what is the partial derivative of r with respect to p. R and p are independent variables, so that's 0. Started with dh by dr. So that's 0. that tells you that this is the h by dp, right? 1 multiplied by that, which is of course true. This is nothing but dr by dt, right? So that's dr by dt. So this is, so maybe I should write this as dr by dt is equal to partial derivative with respect to time. It has no explicit time dependence, so that's 0. And then that's this. So that gives me this, which is of course one of the Hamilton equations of motion. So that's a consistency check if you want. We can do the dp by dt also, but this will come out to be, so you do that, right? And let's do here the L by dt. How does the angular momentum change with time? Of course, you can do angular momentum in r and p. You can explicitly do that, but it can also be done using, this is 0, no explicit dependence in time, plus L, comma h. So you say this is partial derivative of L. One has to be careful with this vector index. There are too many vectors coming up, so you want to put an index there. That is the easiest. This is L, but that's not what is getting dotted with the next one. This is the partial derivative with respect to R that is getting, that is the gradient that is dotting with the next one. So be careful with that. So dotted with the h by dp minus of L with respect to p. What is partial derivative of L with respect to R? So that's equal to R crossed with T. These are vectors. So this leads to the idea that this is 1 crossed with T. Maybe I should come back and do this. There are sufficient details going through this. So I'll come back and do this again. The L by dp similarly is equal to, I should move it to the front first, so it is minus 1 cross with R. I'll work on this again next time. That will be better. Right? Stop instead of hurrying and pushing it. But in your homework, I haven't asked this. I usually ask a scalar, is Lx or Ly. You can do this more explicit. Okay. Thank you.